Intellectus Podcast, abbreviated as the VI Podcast. I'm Harish, and this is
Chris.
We are both graduate students at the University of Waterloo in Canada, affiliated with the Vision and Image Processing Group.
And hence the name.
Our goal is to make top-tier research accessible to all through meaningful conversations with researchers who are well-versed in their craft. Our hope with this podcast is to garner widespread interest in science and academia.
This podcast wouldn't be possible without the immense support from the directors of the VIP Lab, Professor Alexander Wong, Professor David Clausey, Professor John Zelek, and Professor Paul Fieguth. We're both thankful for your encouragement in this endeavor.
Dear friends, let's all grow together. We hope you enjoy this episode.
In today's episode of the Vox Intellectus Podcast, we have a special guest with us, Professor Paul Fieguth, the Vice President of Academic Operations at the University of Waterloo. He's also a co-director in the Vision and Image Processing Lab, the director of the Statistical Image Processing Lab, and a professor since 1996 in the Systems Design Engineering Department at UW. Professor Fieguth is a multifaceted personality with an equal breadth and depth of experiences. He completed his bachelor's degree at Waterloo, his master's and PhD at MIT, held appointments at Oxford and Heidelberg, and 2 postdoctoral positions at the University of Toronto and MIT. He is not just an important administrative figure at Waterloo, but also an active supervisor, teacher, and researcher. His interests span across the theoretical and practical aspects of computer vision, remote sensing, complex systems, statistical modeling, multiscale models, and societal and environmental systems. He has authored 2 very important books. One is in the field of pattern recognition called An Introduction to Pattern Recognition and Machine Learning, and one in statistical imaging called Statistical Image Processing and Multidimensional Modeling. If we were to list all his achievements, we might exceed the time allotted for this podcast episode. So let's let our guests speak to those in the flow of our conversation. Professor Fieguth, it is our great pleasure and honor to have you here. Welcome.
All right. Thank you very much. Great to be here.
So, first we'd like to actually start with a very fundamental and basic lesson. You've been a professor for literally the last 2 decades, more than that, actually, for the last 3 decades. You finished your PhD from MIT, and then you've done your bachelor's here at Waterloo, your master's in MIT again. What is the definition of research according to you, and who do you think is a researcher exactly?
I mean, you can't really have a definition for research. I mean, I suppose research is curiosity-driven thinking, and ideally sort of open-ended questioning from anywhere from sort of very applied and concrete to wildly open-ended and speculative. So we have people doing industrial research. At the same time, we have people doing very analytical, sort of theoretical research. We have people doing sort of computational methods. So I'm not sure I would want to pin it down. And if anything, the one thing that you experience in a little bit in grad school, but certainly when you become a faculty member, is how blurry the lines become. As an undergrad student, things are very concrete. You're either in this program or in that program. You're either an electrical engineer or mechanical engineer, and you kind of know what program you're in, and you know what courses you're getting. The further you go along in academia, the blurrier it becomes. And at some point, the department boundaries, I mean, you kind of know your colleagues, but otherwise, a lot of people you interact with are in other departments. If you look at who's doing machine learning here at Waterloo, it's kind of all over the place. And so then you start to ask yourself, like, do we really need these structures, right? And so, and I say all of that mostly just to emphasize that what research looks like and who does research is much more varied than one might sort of think at first glance, or certainly than the general public, right? I mean, the general public might have a stereotyped notion of person in a lab coat or person hunched over a computer. But truth is that it's fantastically varied. So don't want to repeat myself, but from the very applied to the very computational to the very analytical. And as long as there's a desire to be exploring kind of to some degree open-ended and untested question, we would call it research.
Yeah, so I got to ask this question. That was something that I noticed on your profile, and it blew me away because, your master's degree, you were awarded in 1993, and your PhD were awarded in 1995. It is extremely impressive to have your PhD defended within barely 2 years. I'm really curious, how did you manage that feat?
So, yeah, I mean, there are a few little caveats. So first of all, I finished the master's actually more quickly. So there are two pieces. One is the master's was actually done in December of 92, but graduation only happens once a year. And so therefore it gets listed as being in 93. However, that being said, I did take a term just taking courses and looking around. So the winter of 93, I wasn't yet in the PhD program. Or was that the fall? Doesn't really matter. And the other sort of factoid, I suppose, is that MIT at the time was famous or infamous for people taking forever to get their PhD. That was primarily in computer science, so not so much in electrical engineering, but still, there was kind of this aura. And for me, sort of coming out of Canada, not really wanting to be in the States long term, I had sort of a degree of anxiety about, it's going to take forever. Then with hindsight, I could have stretched out the PhD a little bit. Like I didn't really have a need to do it that quickly, but it was in part driven by this anxiety that, everyone seems to be taking 8 to 10 years to do their PhD. I'd better get my act together. And then indeed, it took just a little bit over 2 years. And I probably could have enjoyed myself a little bit more and just sort of eased up the pace. But yes, otherwise, indeed, I was pretty focused, and it did indeed take only a bit over 2 years.
That's amazing, because most people have the average span for a PhD is like 4 or 5 years at least coming
Right.
from.
Yeah, it's kind of like fixed these days to
Yes.
do a PhD, because most people assume, or at least it's probably factual to an extent, that it takes at least 4 years to do something concrete, especially in the space of AI or computer vision right now that we are working on.
So you would say that this is the focus that essentially helped you get through it so quickly, and a little bit of anxiety, right?
Yeah, I mean, it'll be a variety of factors. I don't know. I was motivated. I was, I'm pretty efficient when it comes to sort of working on things. I'm fairly fast, at least at the time, I suppose, at sort of coding. And so what was more of an impediment to other people to sort of getting things up and running, I did pretty quickly. So you can save yourself a lot of time that way. I had the good fortune, we don't need to get into the details of it, but I ended up setting up my code in a kind of you can't use the word meta anymore because, Facebook sort of took that over, but in a very abstracted kind of way. I mean, it was sort of a hierarchical statistical thing, but the question is, well, what assumptions do you want to bake into it? And so I realized very early on that I was going to end up rewriting it every time one changed the assumptions. And I realized that actually I could write the entire thing more or less just using compiler defines. And then essentially just having a set of definitions of like, what does multiply mean? Like, is it a matrix, a vector? Like, what thing is this? And that allowed the same core piece of code to go all the way from a really simple sort of scalar environment to some like crazy sort of complicated thing, but without any compromise in computational complexity, because if it was a scalar version, all of that happened at compile time, not during runtime with like a whole bunch of checks and so forth. So I think that decision alone probably saved a year because it allowed me to, I ended up doing about 7 versions of the thing. And like I said, the core code was done, but I had 7 versions depending on what sorts of assumptions and degrees of generalization. And you're trying to sort of represent states in a hierarchy, and so ideally you need to do eigen or singular value compositions in order to sort of conditionally decompose a piece of information into sort of multiple sort of chunks. And so you could do that manually, you could do it in an ad hoc kind of way, or you could in fact be taking eigen compositions, and that the same piece of code allowed all 3 to happen. Allowed me to make tremendously faster progress than would otherwise have been the case. So there's that element to it. So some of that was planning and some of that was luck.
That's beautiful. So you've been associated with Waterloo for a pretty long time now, and you've seen it develop over pretty much the last 2 decades. You took a decision to come back to Waterloo after your graduate studies. Why? How did this come about?
Right. So I often tell grad students that I'm bad in terms of offering career advice because I only ever applied to one job and I got it. So after MIT, I came back to Southern Ontario because I wanted to understand. I'll try to not make the answer too long, but there are a variety of nuances to it. So at the time, academic jobs were very, very hard to get. And I saw peers at MIT applying to like literally hundreds of jobs anywhere in the world. And I thought, that's ridiculous. Like I don't need to have academic associated with my name so badly that I'm willing to go anywhere, to any place, any department, in any specialization, just so that I can call myself a faculty member. And so I thought, no, I'm going to go back to Southern Ontario and just see what opportunities look like. And so I had an NSERC postdoc, so I was at University of Toronto, and looking around. So, I wasn't even there that long, but the idea was to spend 2 years understanding the lay of the land, like what are universities doing, what kinds of industries and opportunities are there. You have to remember this was 1995, 96, very, very early days for the internet. So, positions and so forth weren't really advertised on the internet at all. So you're still paging through paper ads and IEEE Spectrum to look for sort of positions. So it was much, much harder to be informed. Incomparably difficult to nowadays. So that's where I was. And coincidentally, without I didn't know anything was coming up, a position in electrical and a position in system design at Waterloo came open in May of 96. I applied to both of them, got interviewed by both of them, and here I am. And so I had not expected that. And the key, like why I was reluctant to sort of put expectations or my sights on it is I read a very influential paper by, I believe, the president of Caltech. It was a paper written late 80s, early 90s, where he pointed out that the university system worldwide had expanded more or less exponentially since Newton's time. And if you understand how exponentials work, it means that over a finite period of time, you get the same amount of growth as you did for the entire past history to minus infinity. And so exponentials are very, very unusual sort of beasts. And what it means is that for 200 years, it was reasonable for most PhD students to get a position in academia. By definition, once you're in steady state, that's simply not possible. In steady state, every professor has to produce one PhD student to replace themselves. Anyways, so that was very clearly articulated in this paper, and that made a big sort of influence on my thinking. And so I would say that alone led me to really sort of change my expectations. Now, in my case, I was fortunate. I got a faculty position. It was great. But I was quite deliberate in not setting that as an expectation or pinning my hopes on it. Now, in terms of why come back to Waterloo, that was the place where the position was. I mean, if there had been a position at another good Ontario university, I might have ended up there. But indeed, it was just an extremely fortunate coincidence that two positions opened up in Waterloo engineering at the same time. And of course, I knew, having studied here, what that looked like. And so I was confident that it would be a great place to be. So there was no worry about that. But in actual fact, faculty positions were few and far between at the time. So it's not like I was looking around all the Ontario universities thinking, I'll apply there. It didn't work that way. So I applied where the positions were.
I see. So was this decision a pre-planned one to stay in academia, to return back into a postdoc position? Was this pre-planned by you when you did your PhD, or was this the paper that influenced you to get back? Because not a lot of people who actually finish their PhDs end up in academia back. There's a large portion, yes, but a lot of them also venture into other areas. For example, becoming an entrepreneur or stuff like that.
Right.
Probably that was not the trend back then. I'm not sure.
Right.
But what drove you to be back in academia? Was it a pre-planned decision, or was it?
Well, yeah, that's a good question. I mean, again, now with internet, the ability for a PhD student to be informed about what opportunities look like, to network with other people, is just completely incomparable. It's night and day to what was happening back then. So there's really no comparison. And I would say when you asked, come back to academia, I mean, I never really left, but the decision was actually much more explicit after my undergrad. So during undergrad, it was co-op, as you would know, or people who understand the Waterloo sort of engineering education model. And every co-op term, I mean, this is obviously slightly exaggerated and summarized, but every co-op term I was sort of neurotic and anxious Because, if you're working for an employer, are they okay with how I'm doing? In every school term, I was happy and well-adjusted because you're kind of your own boss, right? Like on a school term, it's not that every test goes great. It's just, it's your business. Like you know whether you did a good job. And so if you didn't do a good job, you know where you have to improve. And if you did do a good job, you get the feedbacks like, I'm on track. Whereas I found on a work term, I never really know. Like, am I doing a good job? Is this adequate? So I kind of liked the sort of feedback that one got in academia. Now, obviously, as you both would know, as a PhD student, you don't get that kind of regular test, feedback with scores. And so much of what I liked about undergraduate doesn't really persist into grad school. And that's fine. That's part of the learning process. But that being said, I was always fond of the kind of curiosity-driven and creative-driven sort of aspect to academia. That appealed to me greatly. So despite the paper from Caltech, I was super open to the idea of academia. I was just being very deliberate about not making that a prerequisite to my career satisfaction. Because then it'd be easy to imagine you spending the rest of your life sort of with regret or frustrated that somehow I didn't do this, or I didn't study in that area or something like that. I just don't think you can second guess yourself that way. So did I like academics? Absolutely. And I knew I liked teaching, and so I knew the fit would be good. But I also liked a lot of what high tech was about. So I think there are a wide variety of industry positions where I could have actually been quite satisfied and had an interesting career. So I wasn't really tied to academia. But the NSERC postdoc was very convenient. So it pays your salary for 2 years. And so it gave me the opportunity to move back to Southern Ontario and have a 2-year window to sort of figure out what next steps would look like.
It's beautiful. I really like the analogy of treating schoolwork as a business where you get very direct feedback of whether you did a good job or not. You're currently the Associate VP of Academic Operations at UC Waterloo. Some listeners might not be necessarily familiar with the hierarchy here and how that works. So could you briefly explain to them what that role entails?
Sure. I mean, my current role is new, so it's not even for people who've been around the university for decades won't necessarily know what this role is because it didn't exist. But broadly, there are a variety of sort of vice president and associate vice president and associate provost kinds of roles, which are sort of pan-university. That is, they have a responsibility of some aspect of the university as a whole, as opposed to dean, associate dean, and chair roles, which are necessarily within a department or a given faculty. So I have been associate chair and chair in a department. I've been associate dean in a faculty. And so my current position is to oversee a variety of aspects of what it takes for the university to run effectively university-wide. Now, the title academic operations clearly doesn't say very much. I mean, in practical terms, the provost role is an almost impossibly overloaded role. And so in practical terms, I do a certain chunk of what the provost simply doesn't have time to do. And so I'm involved in a wide variety of areas like making some progress on IT and data governance at the university, and looking at certain sort of reviews of space usage. But the really big ones are budget process and planning process for the university. Again, just to be clear, the university already did budgeting and planning, but arguably a little bit disconnected and not quite in as integrated a form as what the president and the provost would like to see happen. And so ideally, I and an office, a support office sort of around me, so to speak, is meant to make significant progress in how we develop a budget model that is fair and effective for the university as a whole, meaning both the faculties and all of the sort of administrative units that work with the faculties to make the university run, and to dovetail that with planning, because the two sort of separated from one another. It's very easy to get cynical about planning because everyone sits in the room, has some great ideas, and you write up a strategic plan, but then kind of that's it, and it dies, and that's terrible. It's also easy to imagine that budgeting is just kind of seat of the pants, like, well, last year went this way, let's propose this. Really connecting the two is where you can make much, much more interesting progress. And it's not just connecting budgeting and planning, it's also connecting different units. So if unit A is articulating an idea that has a budgetary impact on unit B, if you didn't know that, you're just going to end up with stress and frustration. If you do know it, you create the opportunity for these two to be in dialogue and figure out, like, how do we move most efficiently on, like, do we need extra resources in unit B, or does unit A take over some of this, etc. It leads to dialogue. And that's why they refer to integrated planning and budgeting. The integrated part is to really create opportunities and motivations for that kind of dialogue to happen. So there's a whole bunch of other pieces that I get involved in, but I hope, like, I don't want to say too much because you'll probably have other things you want to ask. But in a nutshell, those would be kind of the main things that I'm doing.
Yeah, kind of makes me ask this interesting question to you. Most people see administrative work to be much different than research,
right? And
I believe that is so. Do you think both can coexist, or what is your preference generally? Do you like research, or do you like the administrative work that you do?
Yeah, I mean, well, those are very different questions, right? The one is, what do I like doing, and the other is, can they coexist? So those aren't the same. So, I mean, can they coexist? Well, clearly, administration and research can coexist in the sense that most associate chairs and associate deans still have a research profile. And when I started my current position, it was a little bit out of hand. I think I had like a dozen grad students, which is not what upper administration wanted me to have when I started in the current position. But as you would know, we can't just like magically sort of graduate a bunch of sort of grad students. So that does take some time. So it depends. I mean, the short answer is it depends on the administrative position. So there's nothing inherent about administration. It's more, is it 1 day a week? Is it 3 days a week? Is it 5+ days a week, right? And so it's really much more a question of workload and expectation. So inherently, from a workload perspective, if the hours permit it, absolutely, they're sort of they can coexist. In many ways, they coexist quite happily because the part of your brain that's doing administration is in some ways different from the part of the brain doing research. And so that's not to say that that's a problem. In fact, it's not a problem at all. It means that one activity gives you some degree of relaxation or change from the other. And a change of pace, a change is good as rest kind of thing, right? So after you've done admin for a while, you kind of like the idea of talking with a few PhD students. And after you've been sort of digging through sort of details with PhD students, it's kind of nice to have something very concrete to work on administratively. So can they be compatible? Yes. Do I like both of them? I mean, they offer very different kinds of rewards. The kind of gratification with research, I mean, it varies on the person. I really like working with grad students, so a lot of the gratification is of seeing grad students effectively mentored and becoming more independent over time. My personal opinion is that if I'm micromanaging my grad students, I'm doing them a disservice. The grad students are not really primarily there to do my research or to publish papers for me. I mean, ideally, some of that happens, but really, grad students are there to become more capable and more independent at research. And so if I see that happening, that's great, and that's good. And so there's a gratification that happens there. With administrative work, the gratification is very, very different. It's much more service-oriented. Now, you could say, well, working with grad students is also service, but the feeling is kind of different. So particularly when I was chair and now my current AVP role, you're working with a tremendous variety of people, and there are just a lot of things that need doing. And the university simply needs people who are motivated and willing to take initiative on stuff. In the same way that research offers, really quite wide and open-ended opportunities, in many ways, administration's not that different. I mean, yes, it's not fun in the sexy way of, research having conferences and papers and sort of awards and recognition. So administration suffers in the sense that it's kind of the poor cousin that way. But as far as opportunities go, there's a lot of opportunities. I mean, as chair, as dean, or in my current AVP role, the sky is kind of the limit. Like, what would you like to do with the department? It's not a matter of being autocratic, like I declare the department's going to be this way, but rather listening to your colleagues and hearing all the ideas. Now, like, how would you like to move some of these forward? That's a fantastic opportunity. So it's a lot of work, but it is quite gratifying to create opportunities now more for faculty and staff than necessarily for individual grad students. But to actually make something happen. And so, I mean, a concrete example would be the undergrad biomedical engineering program. Clearly wasn't just me, right? I'm not going to maintain that for a second. But I was chair and brought that to the attention of the dean and said, hey, like, well, in a nutshell, we tried this before, it didn't work. And I wasn't even trying to be pushy. I was just like, help me to understand why it didn't work before, and what might we do differently. And, a number of years later, we've got a biomedical engineering program. I mean, that's amazing. Clearly, a lot of people did a lot of work on it, right? I really want to re-emphasize that it wasn't just me. But I was chair at the time and asked some of the right questions and got something going. And now we have, outstanding stream of students. And the biomed program is crazy hard to get into because there's a fantastic demand for the intersection of engineering and life sciences. Awesome. So
yeah, I think that's an excellent answer, because viewing administration as a complement of research rather than is definitely a viewpoint to look upon, and especially taking a look at both the fields as asking the right questions. I think that's going to be the crux of or the bridge that basically connects both of these.
And we'd want to make sure we get teaching in there too, right? I mean,
Yeah.
Because it's not a matter of research or admin. Very broadly, for all faculty, there's research, teaching, and what we broadly call service. And service tends to be more admin-like, but we need to make sure that we have all three of those and are thinking of the interplay. I mean, teaching also has tremendous opportunities for creativity and open-ended approaches to how we would like to sort of best approach certain material, etc. Clearly, it's very different. I just want to make sure that we...
Oh, treading along those lines, you've been to a bunch of universities, ones that are basically top-notch, top-tier, in Oxford, Heidelberg, MIT, and of course, Waterloo. One of the things that I do want to ask is, how is research basically conducted there that can be implemented over here? Are there any implementations already made? What are the implementations that you think have already been made? Some that can be inspired from there? And what is the general culture from there and here, good, bad, whatever it is? What do you think about both of these?
Yeah, I mean, it's very, very difficult to try to generalize. I mean, in the sense that the vision image processing group where we are here is very energetic and thriving, and so that's fantastic. And so if you were a visitor to this lab, you might reach a conclusion about, quote, Waterloo, but really what you're seeing is this lab and how it happens to work, and you probably shouldn't or wouldn't want to reach conclusions about an entire university from that experience. And so similarly, and on top of that, I mean, I haven't been to Oxford in like nearly 30 years. So how it was then is very likely quite different from how it's now. And I mean, the group with whom I interacted was a particular group in sort of the remote sensing field, and also not indicative necessarily of the university as a whole. It's also geographically spread out, and so you really don't see what it sort of looks like overall. So I would be very reluctant to sort of try to speak to sort of research practices, because I'm just not sure that goes sort of university wide. A couple of comments I will make. One is one's anecdotal. So the one anecdotal one is that this may be more Europe versus North America. But the culture of collegiality and dropping everything and either being with your colleagues over lunch or for tea in the afternoon, that's more Oxford, is just so much more pronounced in Europe. And a lot of Europeans, when they come here, are kind of shocked to see professors eating a sandwich in their office like over lunchtime. But what's also shocking is how quickly people can get used to a system. So, the Europeans, you'd like to think they might change, our way of doing things, but they're eating sandwiches in their office pretty quickly too. And vice versa, when North Americans go over there, they're quite happy to take an hour off for lunch every day. So it seems a bit of a shame that we can't adopt a little bit of the collegiality culture that I have generally seen at European universities. I think that would be great for our mental health and just make it a more enjoyable place to work overall. So that's just one sort of anecdote. But I mean, that was not just me or my host. The director of the lab of some big institute was also at coffee break or tea break every afternoon and was also at, lunchtime. So this was a widespread assumption that, you go for tea or you go for lunch. So it was an exception to be sort of in your office at that time. So that's one little anecdote. The other part I'll mention, there's sort of three thoughts. Number one was sort of that collegiality. Piece number two is the kind of entrepreneurship that you feel here at Waterloo is actually somewhat special. I mean, there are lots of universities that want to do it. I haven't seen it anything like what sort of happens here. And so one doesn't want to take it for granted. It requires nurturing and support. And one also doesn't want to just kind of assume that, happens here. And Canadians like to be sort of down on Canada, right? Like, well, if we do it, well, probably everyone does it. Well, like they tell us that we could never get professors to, blah, 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 blah. And the issue is that here, at the time that you're hired, you know what the deal is, right? You know there's co-op year round. You know the classes are going to be offered in the summer. That's just how it works. And so you don't really spend a lot of time arguing about it. That's just the system. And so it works largely because that's how it has worked. And the same thing for tea breaks and lunchtime collegiality. So just wanting to point out that there's certain things that we might do differently, but there's certain things that we do exceptionally well. The third piece I'll just mention is the one thing that I have said often is I would love for a bit more of a sense of energy when you're walking around the place. And I don't mean for a moment that there isn't great stuff happening, because there is. But when I was at MIT as a grad student, you felt it. And you felt it because it was more visible. You didn't feel it because MIT is so much better or anything like that. Because I see students doing fantastic work here and qualified at the same level that I saw at MIT. So it's not that for a moment. But there was a degree of energy and buzz. When you walked down the hallway in the buildings, you saw stuff. You saw announcements of things. You saw companies coming and wanting to make show a prototype of something, right? And here you kind of you walk down the hallway, all the doors are closed. There's just not the same sense of energy. It's not that things aren't happening. They are happening. We just somehow do a poor job of showing it to ourselves, really. I don't need politicians to know it. I mean, I guess there's good reasons for them to be aware of what we're doing. But what I mean is I want us to be sort of energized by what's happening here. So I've often referred to a sense of energy or buzz or excitement that I just don't perceive as department chair. I felt it. As associate dean, I felt it. But that's because I was connected in. And that was partly my job to be connected in. But as a regular faculty member kind of walking through the university, I just don't feel it the same way. But I know it's there. So I keep saying that because what I don't want is for someone to get mad at me. It's like, we do good work. Yes, we do good work. I just don't think we promote it the same way to have kind of a sense of excitement on campus. Like we should have people in science being excited about what's happening in engineering, and people in engineering excited about what's happening in health. People in health excited about what's happening in arts. We want to kind of break those faculty boundaries. We want a sense, a kind of broader whole of there's amazing things happening at this institution. I don't quite feel that the way I saw it in grad school at MIT.
I see. I mean, you are the co-director of the FIP lab, and you're the head of the statistical image processing lab. Bringing up both of these and maybe more, what were you able to inculcate into these from the regular culture that was followed before? Is there a change that you made in the way that how both these labs functioned under your direction? And is there something that you really would like to implement or improvise upon these? Because one of the things that you talked about is being more energetic as a whole. And I believe, personally I can speak, and Chris can vouch for it because we are from the VIP lab, and
VIP lab
we
is
do
an
have
outlier.
that. Yeah,
Yes.
VIP lab is definitely an outlier, and we do have. We cannot relate to not being energetic because we always have people around doing some or the other stuff, and because we are here, we can speak for it. But of course, there are a bunch of different labs around here which are probably the same. But what are some of the things that you've probably learned along the process of building both of these mini institutions inside the institution of Waterloo?
Right. So, it's not an accident that the VIP Lab is a sort of pretty happening and exciting kind of place, right? It takes a degree of deliberateness. At the same time, I should also be super clear that although my bio sort of lists a sort of statistical image processing lab, some of that's more just organizational. Like really, I'm co-director of the VIP Lab. All my students are members of the VIP Lab. I think just in order to have a web page, they had to give, they had to give me another name. So let's just be clear about that. All of my students are part of the VIP Lab, and that's where my sort of work goes. I don't think that I don't want to take credit for that. Partly it's history, and partly it's accident. So the history is that my predecessor in terms of directing the lab, that was Professor Ed Jernigan, who was also, he was supervisor for Dave Clousey, who's also one of our co-directors. But Ed also was at MIT for his grad school, so he would have had a sense of this. But so there were two key things. One is really a sense of community, and we've tried to really inculcate that all the way along, right? All the VIP Lab directors are very keen to have their grad students collaborate with other grad students. We don't really have a hang up on, please primarily collaborate with students I'm supervising. Like there's none of that. And we have weekly seminars, like there's lots of labs that don't have that. So we're really trying to have a degree of visibility of the students having a sense of community. If the students want to do a thing, like right now there's a volleyball team or whatever, like I love supporting that. Awesome, great. So we'd like to really support initiative. So one big part is just maintaining that momentum and history of the lab as a fun place to be, and where there's a lot of activity. And so we want that hub up to be felt. Like over there through the window, I can see like some big posters, right? We want people to know what other people are doing. And I think the more coincident part, not so much the deliberate one, is where the lab was for many years, predating the building we're in right now, was a kind of a squishy, cramped spot in E2. But when you're in a squishy, kind of cramped spot, it means you know what everyone else is doing. And so having been there for about 20 years, it kind of set the stage, or a kind of an attitude of wanting to know what other people are doing. And wanting to collaborate, because that was it was a noisy, sort of cramped environment. And so, yes, some people complained that it was too noisy, but on the other hand, you always knew what other people were doing. And you had a super clear understanding of what the other projects were. And in the same way that once everyone's going for tea time, you keep going to tea time. Once there's a sense that you take it for granted that, we collaborate with other students, that's what happens in the VIP Lab, that kind of thing persists. And so we've been very fortunate, and not just by accident. All the co-directors were quite deliberate about wanting to maintain that ethos, even after moving here to EC4, where it's less noisy and less cramped. But I routinely tell my students, go to the Friday seminars, please collaborate with other students, chat around to other students when you have questions, because not only to get your questions answered, but I want them to hear what you're working on, because maybe they'll ask questions, maybe you'll end up having some idea that you'd like to sort of follow up on, that kind of thing. And I think when all four co-directors are nudging in the same direction, then things like that happen. But one person on their own, you can scream and yell all you want. If people want to just kind of hide at home in the living room and do their own work, you can't force people to come. So you have to, that kind of culture takes years and years to build. But once you have it, it's tremendously valuable. So I would put it down to decades of culture and expectation in the VIP Lab. And once you have it, you for sure don't want to take it for granted, but it's a lot easier to maintain than it is to build it up from scratch.
Perhaps it also helps that we have an open floor plan office or in cubicles, and we get to chat a lot with other people.
It's kind of like a broader version of the room in E2. In E2, it was even more open because it was just one room, and everyone was sitting at a bunch of desks. Here you're sort of a bit more spaced out, but yes, some of that sort of openness persists here, and absolutely, that I see that as important. The last thing we want is a bunch of people sort of hidden from view from other people, or a little bit tricky to reach because you'd have to knock on a door, or you'd have to walk down the hall, and then here you can just kind of stand up and see who's around.
That's great. So let's maybe move to a little bit of the research topics while we're at it. So one of the areas in which you are considered an expert is complex systems. To our listeners who probably are scared hearing the term complex, could you explain what a complex system is? What makes it so interesting to study and to research?
Right. Well, I'll have to correct one major error in your introduction because you referred to two textbooks, but there is the machine learning one and the statistical image processing one. But my favorite one is the complex systems book. So.
I must have missed that. This is not listed anywhere.
Oh, well, it's definitely listed somewhere, but...
well, it's not listed on the profile.
Okay, well,
What is it called as exactly?
What's that?
Is it called as complex systems?
It's called an Introduction to Complex Systems, and, there's the original one, there's a second edition, so if anyone's going to look it up...
We'll put that up on the podcast.
Yeah, you want to look it up. If it's UW students listening to the podcast, they can get the book for free in electronic form from the library, so it's very, very easy to find. Complex systems are awesome. So that's become kind of like my little passion project, so to speak. 12 years ago, we didn't have a course in complex systems, or maybe 20 by now, I don't know. And as it often goes in academia, so I was pointing out that, we have this kind of gap, and people said, yeah, good idea, why don't you do it, kind of thing, right? So it wasn't really my background. I had studied some of that material, but I wasn't really a complex systems person. But neither was anyone else. I don't mean the whole university, but certainly in my department. So I sort of took it upon myself to create the course. It took a few years to sort of get it actually more or less in shape. And then, eventually a textbook, and then, it gets further refined over time. Now, that wasn't your question. So what's a complex system? First of all, we want to distinguish between complex as opposed to complicated. I know that may be sounding like I'm splitting hairs, but we need to do that because complex is maybe poorly chosen because it doesn't necessarily mean difficult. I reserve the word complicated for that, just because if you're going to teach a whole course on complex systems, you have to be able to sort of choose your words carefully. So there are lots of things that are simple. There are lots of things that are complicated. A complex system could be either one. So a complex system is, well, let me first give the definition and then we'll see why it matters. So it tends, in general, is the interaction of many pieces and where the nature of the interaction is nonlinear. So I have nonlinear, many elements, and interacting. Okay? Those are the three. I just want to make sure I got that right. Did I say one twice? Interacting, many, nonlinear. There you go. So they show up all over in nature, biology, computer science. And so what makes them fun is that it can go anywhere from the whimsical to like the massive, and anything from like a really simple sort of mathematical analysis to almost impossibly difficult. But what I love is the fact that just walking around, you can sort of see these all over if you know what to look for. And yet, even after teaching it for years, it'd be embarrassing from time to time in that I wouldn't recognize it even if it's staring me in the face. And so what makes them so tantalizing is that they can be right in front of you, and in principle, you should know what's going on, and yet they're sort of counterintuitive. So the complex part is more the counterintuitive and not so much really difficult. So I do teach it at the undergrad level, and so it's meant to be accessible to sort of third-year engineering students. So the material itself is not impossible, but it can be hard to wrap your head around. Okay, enough of sort of the vagueness. So to get a little bit more concrete, there are loads of things where we have many pieces interacting. So some of the classical ones would be termite mounds. Got 10,000 termites in a big hill, or ant hills, bee colonies, sort of flocks of birds. So anyone sort of in North America sort of looks up at the sky, you'll see birds sort of in kind of complicated sort of forms sort of following each other. That's a great example of complex system. Human consciousness is kind of the ultimate one. So an individual neuron is a nearly sort of inconsequential unit. We have studied it greatly. We know the chemistry, the biochemistry of it in significant detail. And yet you put some number of trillions of them together. Their interactions are clearly nonlinear. There are clearly very many parts, and almost impossible to wrap your head around. Consciousness, emerges. And so in the same way that an ant colony can solve basic optimization problems, and bees can do complicated dances, an individual bee doesn't really know what it's doing. In the same way that an individual termite doesn't really know how to build a mound, but an entire colony of termite builds a complicated mound with ventilation shafts, in the same way that a flock of birds is sort of performing this unusual undulating sort of dance in the sky, but no one bird is controlling it. And so that's the delightful side of complex systems. Now, all of those were examples of many, many elements, and what a property is what we call emergence. That's kind of the sexy sort of swarm side of complex systems. But there are much more sort of simple ones like kind of spinning a top on a table. Is something stable or unstable? If I have a block on a table, like a water bottle here in front of me, that's a good one. Like a water bottle flip that people were doing a couple of years ago. That's a good example of a nonlinear dynamic. So it doesn't need to be consciousness or, the world sort of ecosystem. It can be much, much more concrete things like playing with blocks or throwing a water bottle.
That's an amazing explanation of complex systems. And like you said, they don't need to be complicated.
So the only thing I sort of do want to sort of briefly sort of highlight. So one of my, if you want to call it hang-ups or passions or motivations. So complex systems are characterized by problems which are many element, nonlinear, and have characterized by non-Gaussian statistics. Overwhelmingly, 99% of the material that students see in both undergrad and grad studies is linear, few elements, and Gaussian. And so the juxtaposition between those two short lists hopefully makes it clear why I see this gulf almost in our understanding. And yet basic complex systems aren't that difficult. But what it means is, as a student, if you have grown up thinking that much of what you see on the blackboard, which is analytical by nature, because that's what allows to be taught on the blackboard, and there's reasons why Gaussian statistics are in fact very common, sort of central limit theorem and things like that. So it's not that professors are, unaware. I mean, Gaussians do show up all over the place, but we have so little practice in even having our eyes open for what this other sort of world might be about. So challenging the few element, linear, Gaussian sort of mantra to at least exposing students to recognizing the hallmarks of what happens if I have many element interacting nonlinear, non-Gaussian. So what I'm trying to be clear about is I don't expect such students to sort of do their own analysis and derive things from first principles. That's crazy difficult. What I want is a degree of humility so that when you see one of the telltale signs of complex systems, a little reminder bell goes off in your head where you go, uh-oh, I think I probably want to take a step back and look at this more closely. That is my goal. Because to do the analysis of nonlinear systems is crazy difficult. And that's not what I teach. What I teach is knowing the telltale signs of what such systems do. And so without getting into the details, for which we won't have time, although it would be a ton of fun, linear systems, for example, can only ever have one equilibrium point. And so, whereas nonlinear systems can be bistable. And so like a simple, like any kind of, like a memory element, storing a bit of 0 or 1 must be nonlinear. You can't do that with a linear system, no matter how hard you try. And so there are loads of examples of where people simply had trouble wrapping their head around. I'm part of me is torn. I want to give you an example. Part of me realizes you have other questions you want to ask. But it's counterintuitive. And if you expect things to have equilibria and to sort of behave in linear sort of terms, then you will find yourself almost unable to wrap your head around why the system is behaving strangely. And yet it is truly no more complicated than playing with a wooden block on a table.
I mean, this is a very fascinating area to think about. I mean, it opens up a lot of tangents, but one of the most pressing tangents I have from your advice is to ask, nature in general has evolved to become a really complex entity in itself. So, for example, the mounds that termites build, or all the examples that you gave until now, has been a byproduct of nature, as long as I can infer, or humankind can infer. Do you think one distinguishing factor that separates men from the rest of the food chain, to say, or from the rest of the species, is its ability to comprehend complex systems, and whether man can evolve to reach a level of complexity that can, to an extent, mimic nature, or not even mimic nature, but can be defined in human terms itself?
I mean, that's a super open-ended question.
Yeah, it is.
And there's a lot to unpack there. I mean, I'm not an anthropologist, and so I would be reluctant to try to make claims about sort of what makes humans distinct from. I mean, obviously, we know a lot of what makes humans distinct from other animals, but I would be reluctant to try to sort of put my finger on it and sort of call it complex systems. I mean, my personal feeling is that a big part that makes us unique is actually our ability in our brain, to simulate. We're able to simulate the future, right? And so we understand consequences of actions that most other life forms cannot. So I think essentially the ability to simulate the world around us is probably closer to one of our sort of key, sort of unique attributes. It is true that complex systems are like almost universally distributed throughout nature, but I'm not convinced that human beings are complex systems also. I gave the example of consciousness. There are many others in our bodies, but I'm not sure that makes us unique, because how brains work in other animals are also complex systems. Our ability, as in humankind's ability to tap into complex systems, is a big part of our, reluctant to use the word success, because there's an awful lot of sort of environmental destruction and sort of mess that we're making on the planet. But a great deal of the ability of humankind over the sort of millennia has indeed been the ability to tap into that. But I'm not sure that's unique to complex systems per se, because there are lots of things that we do. You could say that oil extraction and burning isn't really a complex system. There are some fairly simple positive feedback loops. Like if I start a small fire, I can make a bigger fire. That's positive feedback. That's linear. So anything characterized by an exponential is your classic linear system, and lots of things that humans do are actually more exponential-like. So I would say that it's more that humankind lives well in proximity to complex systems, but I'm not sure that we've uniquely sort of wrapped our heads around them. In fact, I would argue that that's been one of our big failures, is that we're not good at wrapping our head around them, that much of our existence has been linear Gaussian. If you look at the distribution of heights of people, kind of Gaussian-ish. If you look at the distribution of strengths of people, so if you're a hunter-gatherer and you have to sort of figure out how many berries can I gather, or how much can I do in a day, that's kind of Gaussian-ish, right? The difference between the strongest and the weakest person is only so much. And so for most of our history, things have been relatively predictable and have relatively clear equilibria. Most of the challenges facing us now aren't that, right? The whole climate crisis is precisely about there being multiple equilibria and tipping points and so forth. That's the hallmark of nonlinear dynamics, right? If the world environment were a linear system, it would be a lot more reassuring, because you can't get tipping points. I mean, the whole point of a tipping point is that you have a bistable system, and so it could tip from A to B and then not tip back, right? That means you have memory. And memory comes from nonlinearity. So, in fact, an awful lot of what we're not good at, same thing with extinction, right? So extinction events and tipping points and all that kind of stuff, that's all nonlinear dynamics. Humankind is not very good at that. So I guess in a nutshell, I would say what makes us unique is the ability to simulate and what we haven't mastered is a sufficiently mature or nuanced understanding of the complex systems around us.
Do you believe that modeling those complex systems with tools like machine learning or AI is a way to at least arrive at approximate solutions that...
Yeah. So, sorry to cut you off. I mean, now we're getting into like a really meaty problem that kind of brings sort of research, AI, machine learning, and complex systems all together. And just in case people weren't familiar, what you're asking is along the lines of, well, if I had some kind of complex system, like let's say, fluid dynamics, and simulating fluid dynamics, pretty difficult. It's a pretty complicated sort of nonlinear partial differential equation. And so you could say, well, what if I had enough examples, like millions of examples of fluid, and I trained a network on it? Could the network then essentially do an effective job of simulating fluid dynamics? So I'm a little bit torn. So part of me thinks no, like the network, it can mimic fluid dynamics, but I guess the one challenge is always the testability one. Like it could maybe do something realistic, 9 times out of 10 or 99 out of 100 or 999 out of 1,000, but every now and then it will just include or encounter a fluid sort of scenario that it had never been trained on, something stupid. So that's kind of my gut sense, but that doesn't mean I'm right, because in fact, my gut sense was that these methods would be far poorer than they've proven to be. And in fact, a lot of people have had quite good success in approaching physics problems, including nonlinear ones, with networks, a degree of success much greater than I would have expected. So I think I've sort of proven myself to not be sort of a good forecaster on things like that. So I'll still stick with, maybe I'm just old-fashioned, like when I was growing up, if you had a computational problem, you approached it computationally. And this business of having a network just kind of, figure out what the computation should be somehow seems like you can't get something for nothing, right? There's like a no free lunch theorem, right? Like you can't get a network doing few computations. I mean, they're still big, but you can't get a network doing fewer computations, somehow getting at things for free. And yet people have clearly had significant success. So I will end that one with kind of a cagey, there has been a great deal of success, but I am worried about like the extreme tail events. And so we don't necessarily have to get distracted there, but in the same way that complex systems, I mentioned this business about non-Gaussianity. Well, the non-Gaussian part tends to be extreme tail outliers, which, some of your listeners may understand, like black swan events in finance or extreme weather events, things like that. So we can talk about that if you want, although that's probably a whole separate podcast. But nevertheless, extreme outlier events are very, very challenging for a network because networks learn on the basis of having like an almost like nearly inexhaustible set of examples to learn from. And if those examples are representative of the whole, then we can do good learning. But if they are not, then the question is, to what extent is the network actually able to generalize to scenarios that were rarely or never seen? And so normally in machine learning, we would say, well, hey, the network has never seen a given scenario. How can I expect it to work? Well, that's precisely what you're expecting networks to do if you give them nonlinear dynamic problems, because they are characterized by extreme outliers, and there are rare events like the once in 100-year flood or storm, or whatever the issue is. And so I would want to be very, very careful. This is the little humility bell going off in my head, is are we actually confident that we can test a given network on its ability to perform meaningfully in contexts where one of these outlying, exceptionally rare, once in a million year events are presented?
That is a lot to unpack.
Yeah. We definitely need another episode in order to unpack all these stuff.
Yes.
We
yes.
at this point.
Or you guys can sort of quickly speed read the complex systems book, and
We are going to do that.
That's actually because I've read your introduction to machine learning book. That's
Right.
how I know of it.
Right.
The only one that is listed on your profile, I think, is the statistical
Right. Well, that's
analysis.
a huge omission because
Yes.
the most fun book is the complex system one.
I truly apologize for the
No
submission.
apologies. But it's the range of examples is what makes it fun. And so, like, I refer to like a block or a water bottle on a table, but it also includes toys like little sort of candle boats, like puppet boats, or like those sort of bimetallic strips that sort of flip, or the slap bands, if you know what I mean, like that people use. That kind of stuff. All of those are nonlinear dynamic or bistable systems. It includes like all kinds of things about the human body. So, for example, like the human skin has hysteresis. Sounds very complicated, but all it means is that if I push my nail into my thumb, a few seconds later I can still see it. So I clearly have hysteresis. I have a non-reversible system. Like it's whether it's the human body or the world around you, or looking at snowflakes, or looking at the sky, or looking at sort of flocks of birds or ants. So the world is just replete with fabulous examples of nonlinear dynamic complex systems. And so that's what I just find so fascinating and engaging, is like you barely need to scratch the surface, and there are examples all around you, like traffic jams. So that's my, the examples I've just been sort of working on were variable stars, right? So anything that's variable in the absence of a variable excitation has to be nonlinear. You can't make things variable from a constant supply. So like any kind of buzzer, alarm, oscillator, metronome, they're all nonlinear. They can't be linear. If you walk by a marina and you hear like by the sailboats, like the mast, like the cables go bang, 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 you've heard that, right? So the wind is blowing steadily, the cables are going bang, bang, bang. There has to be a nonlinearity. Now, you'd have to be a fluid dynamics or aerodynamics person to really know the details, but you see where I'm going with this? Which is, it's everywhere, and B, the fact that the wind is blowing steadily and the cables are banging periodically tells you there's a nonlinear system going on, right? It doesn't mean that you're an expert at it. You don't know how to simulate it, but you know it's there. And so if for your job you needed to do something related to such a system and you observe this, you'd say, I'd better take a step back and find myself a really smart person who knows, fluid dynamics, aerodynamics, whatever, before I make too many assumptions. So it's recognizing the telltale signs that I find so fascinating. The explanations are often complicated. Well, that's fine. But if the sign is like staring you in the face, that's the fascinating part. You can spend a lifetime walking by marinas and hearing that banging sound and never really wrapping your head around what's that telling you. That's what I think is so fascinating.
Yeah, and it touches upon the fact that a lot of beauty lies in those systems.
Absolutely. Yeah,
a lot of beauty. I would like to ask you, because we are shortly running out of time. I would like to ask you for advice, general advice for students like myself. Essentially, like when you're looking, for example, at prospective students who are joining a research program, what are the core characteristics that you're looking at, and what values would you look in those individuals?
Yeah, wow, advice. So that's one always has to be very careful in offering advice. So, but at least your question was a little bit more focused. So in terms of prospective students, I mean, what I, as a supervisor, the number one thing that I would want, I mean, clearly there's a certain technical ability. So let's say there's a few things. So there has to be technical competence, right? And that would be both on, let me talk even more specifically about my own domain, right? Because I don't want to sort of make claims about grad students in general. So I would need a student who has at least a degree of comfort with mathematics. Not that I need them to do serious analytical work, but I have found, let's say over the last 30, 40 years, students are much more inclined now to go straight to an algorithm, right? And just like get an algorithmic solution. Well, you can't really do research that way. That's kind of more ad hoc, kind of hacking approach to research, which is, get an algorithm to try this, try that. You need to think about the problem. And my maybe limited exposure, but in general, students are less inclined to formulate a problem, to think about a problem analytically, or to sketch a problem. So if I had to boil it down to a few things, like if a student can sketch, like take some kind of function and sketch it, in my mind, there is a translation from the abstract to the more concrete. That's important to me. So I need that translational ability, I need programming ability, and I need curiosity. And of course, some of those are very hard to measure. So for a given grad student, you don't necessarily know. But those are the values I really try to push. And so, if you talk to my students, you'll know that I'm constantly whining about, wanting to see sort of notation and formulation, like formulate the problem, right? I don't want to, they're invariably telling me the solution. I don't want to know the solution. Formulate the problem, because until you formulate it, you don't actually know what are you dealing with. Are you even solving the right problem? And if you can't draw me a sketch of part of it, then I'm not sure that you really know like what you're dealing with. So I would say, like, I need the programming competence, but I am reluctant, or I'm a little anxious when students go there too quickly. So programming, sort of analytical ability, and curiosity. And there has to be, and I guess maybe a fourth one is related to curiosity. Students have to kind of like academics. You have to, the kind of person who likes taking courses, right? If you don't like taking courses, then I'm not sure you're going to like grad school. I mean, there's some people who go to grad school because they, a certain job. I see the same thing in undergrad, right? I was associate chair undergrad and then department chair for a long time. And you have a university open house, and some parent would come and say, "What job will my child get after graduation?" I'm thinking, graduation is 5 years away, right? And I'm looking at some 16-year-old. I'm thinking, you're going to be here for like what now at this point is like a third of your life, right? So I would always tell them, like, pick something you want to do, right? Don't study for 5 years because of the job you might get afterwards. Like that, in my mind, is a terrible reason. I mean, obviously you want to be able to be set up for a job. Don't get me wrong, right? I mean, a good career direction is important, but we get a good job because we're passionate about an area and we really like studying a given thing, and so therefore we get good at it. We don't get a job because we got something printed on a piece of paper. And so same thing for grad studies. I mean, yes, it opens up doors and opens up possibilities, but I primarily encourage people to go to grad studies because they want to learn something. They want to have a degree of independence. They'd like to sort of pursue something longer than, like in an undergrad course, things are always really tight schedule. Like, submit, your outline today and your project in 3 weeks. Boom, that's it. In grad school, we can develop an idea for a much longer period of time, and we can take some wrong directions. Grad school is really, aside from retirement, grad school is this unique part of your life where if you discover something, I don't mean discover in research sense, if you encounter something really fascinating, like my textbook, and you want to spend 2 weeks reading it, no one really will give you a hard time about it, right? I mean, you can't spend 2 years getting distracted, but if you spend 1 week because something like really caught your mind and like, this is awesome, I want to learn about this, you can do that, right? In undergrad, you can't really disappear for a week. If you have a job where you have like, some kind of like a sprint, you can't disappear for a week. So grad school is this unique part of your life, like I said, aside from retirement, where you can kind of have this ability or opportunity to really explore the things that interest you. And then, of course, shaped by the demands of the institution, you got to take a certain number of courses, and your supervisor will have certain expectations, but you have a lot of freedom. So I would look for students who will thrive in that environment. That would maybe be the end to the answer, right? Because ultimately, the student needs to do well in grad school, right? And so the kind of student who's looking for a job, it's like, I mean, I want to support you, but that's not really the kind of student that I'm looking for. The kind of student who has ideas and had some projects, and the projects were frustrating, incomplete, and they'd like to sort of keep working on them. I mean, I can't guarantee they'll work on all of them, but that's the kind of student that's like, yeah, we can do something with that kind of enthusiasm.
One derivative of this question and the answer that you gave is, how can students or people who are already in their grad school, or some who are aspiring to be so, nurture these skills that you mentioned currently? And in general, maybe to be very specific, if you had to look back at yourself 3 decades before, what will you advise Paul Fieguth, who's in his grad school right now? after your 3 decades of experience?
Yeah. Oh, I have loads of advice for myself.
Yeah.
And not all of it applies to now.
Yeah.
Just again, I mean, I've already said this twice, but the internet now allows you to be informed in ways that were incomparable to when I was in undergrad. The main advice that I would have for myself coming between undergrad and grad school was to be a little bit more willing to think outside the box. I don't mean that I was terribly constrained. It's just, I did my undergrad in electrical engineering, so I assumed, well, then I guess you do grad school in electrical engineering. Once you become a professor, as I mentioned, earlier in our conversation today, the lines between departments and faculties become so much more blurry. So now, if some physics undergrad student were to come to me and say, can I do grad studies? I'd say, yeah, sure, right? Whereas at the time, I did electrical engineering undergrad, so I thought I was kind of like, I'm more or less qualified to do electrical engineering grad school. I mean, that now sounds so ridiculous and quaint. So number one advice would be think a bit outside the box. That's the advice to me in undergrad. The advice to me in grad school, we already alluded to the fact that I was kind of, anxious about it taking forever, and then it took, 2 years. So it would have been, relax a little. I don't mean relax as in, sit back, but relax mentally and allow certain problems to be developed a little bit more. I think I was a bit guilty at the time of what I was just criticizing a minute ago, which was I was the kind of student who was going a little bit too quickly to the programming answer, right? Like, because that was kind of my thing. Like in high school, undergrad, I could program anything. Like, there was something you need doing, I could program that. And so that kind of became my go-to. And I'm not sure that was the most helpful in grad school. So I would have cautioned, take kind of a couple steps back from the I can program that and think a little bit more about developing the problem. So those are the advice to me back then. The advice now, there's endless opportunities for students who want to get engaged. I mean, if you're a Waterloo undergrad student, there are undergrad research assistantships, basically where you can sort of either volunteer or work part-time in a lab. Most universities offer things like that. So there are loads of opportunities to get involved. If you're a keen, motivated undergrad student, honestly, the risk to the supervisor, by risk, I mean like the liability, like how many hours of time we spend and how much money it costs us is quite small. And so in general, most professors are really quite keen to have undergrads involved in some way. We just need to keep our expectations modest on both sides. The professor shouldn't expect too much and the undergrad student shouldn't expect too much, but sometimes it really works out well. But it's a great way of sort of seeing what life is like as a grad student. That's kind of the place I would start. The other advice I would have both for undergrads and grads is nurture curiosity, like whatever form that takes for you. And that will be very different for different people. So I don't want to come across as prescriptive. But honestly, creativity and open-mindedness and challenging yourself and wanting to learn a variety of things, I think is just crazy healthy. So I may have overdone it a little bit. So in undergrad, here in engineering, you can take options, kind of like minors. And so, I started the computer science minor. I also started the math minor. I also did, option rather. I did the physics one. So like I saw myself as wanting to do all three of those. It was unrealistic. But I had this burning desire. It's like, but they're all such great fields. I would like students to want that or want something like that. So because really academia, if nothing else, is there isn't a lot of red tape. Like often students think there's a lot of rules. There are some rules, but honestly, mostly it's about, what would you like to do? So as a grad student, as an undergrad student, like the possibilities are endless. Like there's tons of courses, there's tons of neat opportunities. And so avail yourself of them because, later on in life, it's you just don't have that kind of variety. So anyways, cultivate a curiosity and a sort of desire to sort of expand your mind.
That's an amazing answer. Well, on that note, we will have to finish because we're out of time. It's already 3:20. So thank you so much for joining us and for spending this time with us and talking to us and answering all our involved questions. And we're really hoping for perhaps another run another time because there's so much more that we could ask you and there's so much more behind the person that we would like to get to know. We also have questions about hobbies, which we didn't get to ask.
This episode is more like a prologue to
hopefully,
Fieguth, I guess.
Right. Well, we could do a second run. There are maybe some complex systems kinds of things that one could come a little bit prepared. Yes, there would be some hobby things to talk about. Although how much your listeners really want to listen to me talk about that, maybe you have to get some feedback from this one first, and then you can know how much people really want to listen to me. But if people want to, then I'm more than happy to come and chat with you guys another time.
Well,
We definitely hope they do.
at least our friends in
least we
VipLab
do.
are going to listen to it.
All right. Thanks
Right.
a lot for your
Thank you
time
so much.
and talking with us. Thanks a
Okay.
lot.
All right. You're very welcome.